Okay, so review question 5. The question starts off saying a fluid X with viscosity eta. So the fact that we're mentioning viscosity, we're sort of cueing in that we're dealing with viscous fluid flow or non-ideal fluids. It flows through a pipe A at a rate Q. Pipe A has a length L and a diameter D. Fluid Y with viscosity 2 eta flows through pipe B at a rate of 3Q. Pipe A has a length of L over 2 and a diameter 4/5 D. What's the ratio of the pressure difference across pipe A to that of across pipe B? So lots of quantities to consider here in this problem, and it's a ratio type problem. So I'm going to start with just this writing down like what is the pressure difference. And we usually have the pressure difference written in terms of the radius. So if I start, I guess, with Poisson's equation in terms of Q, the way it's written in probably in the equation sheet or certainly in the textbook, delta P pi r to the 4 over 8 eta L. We can write this in terms of the diameter by just knowing that the radius is diameter over 2. So we can write this as delta P pi d over 2 raised to the 4 over 8 eta L. This becomes delta P pi d to the 4. 2 times 2 is 4 times 2 is 8 times 2 is 16. All divided by 8 eta L. And that 16 is really going to come down to the bottom here. And then we can write this as delta P pi d to the 4. 8 times 16 is 128 eta L. Okay, so you can describe it as delta P pi r to the 4 over 8 eta L, or delta P pi d to the 4 over 128 eta L. Now these are equations for Q, and we want a ratio of the delta P's. So I can write the delta P in this case then, of course, rearrange for delta P. I've got Q times 128 eta L, all divided by pi d to the 4. Okay. Alright. So what I want to do is set up a ratio for pipe A to pipe B, and then consider the terms. Okay. So I'm going to do delta P of A over delta P of B. So this is going to be I'm going to write the fraction here for A. When I'm dividing by the fraction for B, when I divide a fraction by a fraction, turn the other fraction upside down and multiply. So I'm going to write this first term here for A. So A has a flow rate of Q. The 128 is going to cancel. Pipe A has a eta of eta. It has a length L. So everything looks nice for pipe A. Everything's sort of written just in terms of pipe A. Now if I divide by this quantity for B, it's really like turning this fraction upside down and multiplying. So again we have a pi, this is for B. Its D though for B is 4/5. So we have 4/5 of D raised to the 4. We have a flow rate of 3 Qs. We have a 128, that's just a constant. Its eta is 2 eta. Let's just separate those. And it has a length of L over 2. Okay. So now we're going to go ahead and sort of cancel some common terms here, clean this up a little bit. So see what I'm doing here. Okay, so let's go ahead and get rid of those Q terms. Get rid of the pi's. The 128 can go. The eta can go. The L can go. And then I'll do that pinning up here. And this 2 eta times this L over 2, these 2's can also go on this side of the equation. So what am I left with? So delta PA over delta PB is equal to 4/5 of d to the 4 we want to raise that, and then we have this, we're left with a 3 underneath. Okay, so if you figure out this piece out, this ends up being 0.41. Oh, and I don't want to forget over this d over 4 over here. And 4, 1, d to the 4, and I've got this 3 and d to the 4 here. So that's where my d to the 4s will cancel. And 0.41 over 3 is about 1.4. Yeah, 0.14. So choice A. So the pressure difference across pipe A is only 14% of the pressure difference across pipe B. And, so I'm guessing the fluid flows would, if we think about this sort of conceptually, if I draw this out, if we think about pipe A, so it's got a length L, length L, a diameter D, it's got a, sorry, I can't see this, just trying to sketch this qualitatively, value of eta, fluid, and that gives us a certain flow rate Q for a given value of delta P. And then pipe B, we've got a smaller diameter, and it's a longer pipe. No, it's half the length. But because the pressure difference in the center scaling is a function of d to the 4, even though it only goes to 4/5 the length, the power 4 makes a significant difference. We're also trying to push through a higher density, a higher viscosity fluid. And at a higher flow rate. So we can see here from this expression that delta P is proportional to Q, proportional to eta. So we're basically increasing the flow rate for B 3 times. We're increasing eta by a factor of 2. It's inversely proportional to d to the 4. So we should expect that the delta P for pipe B to be significantly higher than pipe A, or vice versa, to say that A pressure difference across pipe A should only be, again, a smaller value. And given that the 2 terms in the numerator, both the Q and the eta, and we forgot about the L over 2. The L over 2 term will come down to the bottom. But I guess the eta and the L term cancel, so we've got 3 times the flow rate. But this 4/5 raised to the 4 is going to be the one that has the significant impact, making a sense for viscous fluid. Changing the diameter or radius have very significant impacts due to the factor of to the power of 4 here.